Welcome back, everyone. So today we're going to wrap up our study on statistics. And today what we're going to talk about is normal distribution. Okay, when we talk about normal distribution, what we're saying is, remember when we studied dot plots and we talked about the shape of the data set after we created our dot plots, and it could be either one of three things. It could be skewed left, skewed right, or symmetric. Well, in normal distributions, the distribution of our data set is going to be symmetric. So we have a cluster, the majority of our data is going to be in a cluster in the middle, and then we have a tail on each end. Okay, and that's what the normal distribution is. It's a bell-shaped symmetric distribution with a tail on each end. Okay, and these normal curves that we're going to talk about have certain properties. The first property is that within one standard deviation from the mean, we have 68% of our data. Okay, and so remember, standard deviation is the difference or the distance between our actual data value and the mean value for our set of data. Okay, and so let's grab the highlighter here so that I can show you all of the different parts. Okay, so 68% of our data fall within one. So within this curve, this part of our normal curve, that's 68% of our data. Okay, and then within two standard deviations from the mean, we have 98% of our data. So that includes the 68% that I just mentioned within one standard deviation plus about 17, no, sorry, not 17. It's going to be 27% more of our data. And then if we talk about three standard deviations from the mean, we include 99.7% of our data. So that's the majority of our data that we're looking at when we're talking about three standard deviations from the mean. Okay. Now let's look at an actual example where we have to put where we have to utilize our normal curve or our bell curve. Okay, so we have this table that gives the birth mass for a group of babies at Bellevue Hospital. All right, and so here we have our set of data with the different birth mass of all these babies in kilograms. Okay, and so I've set it up for you in a frequency table, and I've also went ahead and I've made the relative frequency histogram for you. So remember, this is, as we can see with the histogram, remember our characteristic or our category is going to be on the x-axis, and the frequency is always on the y-axis. Okay, and so what we're going to do is we're going to create from this frequency, from our frequency table, a relative frequency table. And so I've already started that here. So we know that, remember, to get the relative frequency, it's the cell frequency over the total frequency. And so in this case, our total frequency is 20. Okay, so we have 20. Taking the sum of these, of all our individual frequencies, we get a total frequency of 20. Okay, so for 3.3, it's going to be 0.1. For 3.4, it's going to be 0.2, and I've already calculated these. Okay, 3.5 is 0.3, 3.6 is 0.2, 3.7 is 0.1, and 3.8 is 0.05. And as you can tell from your frequency, relative frequency table, that our data is, or the distribution of our data is symmetric, because in the middle is 0.3, and on both ends we have 0.2, 0.1, and 0.05. Okay, and so we want to answer some things from this information that we're given from the histogram and the relative frequency table. The first thing we want to find out is by how many standard deviations does a birth mass of 3.2 kilograms differ from the mean. Okay, and so I've already gone ahead, and what you would do, remember, when you want to find the mean, you would input this data set in your calculator, and you would do your one variable statistics and find the mean and the standard deviation from that. Okay, and so the mean for this data set is 3.5. and the standard deviation for this data set is 0.14. Okay, and so what we're going to do, if we want to find out how many standard deviations does a birth mass of 3.2 differ from the mean, or how much is that distance, what we want to do is we want to find the distance between the mean and the actual birth mass. Okay, and so that's going to be 3.5 minus 3.2, which is going to give us a distance of 0.3 or a difference of 0.3 kilograms. Okay, and so to find how many standard deviations this is away from the mean of 3.5, we want to take this distance and we want to divide it by our standard deviation, which is 0.14. And when we do that, we get approximately 2.1. Okay, so this tells me that my birth mass of 3.2 kilograms is approximately 2.1 standard deviations away from the mean of 3.5. Okay, and now we want to identify the interval of values that are within 1 standard deviation. So we know that this mass of 3.2 is within is approximately 2.1 standard deviations away from the mass of 3.5. Now we want to identify the interval of values that are within 1 standard deviation of the mean. So we know that our mean is 3.5, and we want to go 1 standard deviation away from that on both sides. Because remember, when we have our our normal distribution curve, or our bell curve, we go 1 standard deviation below and 1 standard deviation above. Okay, so in order to do that, we already know our standard deviation is 0.4 or 0.14. So what we're going to do, in order to go below, we need to subtract 0.14, and we get 3.36 kilograms. And we need to go 1 standard deviation above the 3.5 mean. Okay, so we're going to add 0.14. And we get a total of 3.64 kilograms. Okay, and so that tells me that my interval should be between 3.36 kilograms and 3.64 kilograms. All right, and now we want to find out, using our frequency table, what percent of values in the data set are in this interval of 3.36 to 3.64. So going back to our frequency table, if we want 3.36, we're going to be in the 3.34, 3.35 is fine, and we want to go to 3.64, which is here. We can't use 3.7 because that's greater than 3.64, and we can't use 3.3 because that's less than 3.36. So if I take the sum of these, I get 6 and 4 is 10, and 14, I get 14. Okay, so I want to find out, so we have 14 values that are in that range out of the total 20 values. And so that approximately gives us 70% of the values are in this range, are in this range of, or set of values from 3.36 kilograms to 3.64 kilograms. Okay. Now let's look at another example where we have to use, we're going to use a different normal curve. So we've seen where they just give us the total percentages. Now this normal curve to the left is the same normal curve that you see to the right that we saw in the first slide, except it breaks down the percentages in a more detailed manner. So within 1 standard deviation, we know we have 68%. So if we have that, this middle line represents our mean value. And then one standard deviation below our mean is 34% of our data. One standard deviation above our mean is 34% of our data, which gives us within that same 68% of our data within one standard deviation. Okay, so this is just a more detailed normal curve. All right, so we have the masses in grams of pennies minted in the United States after 1982 are normally distributed within a mean of 250 grams and a standard deviation of 0.02 grams. So we know that our mean, or our X bar, is 2.50 grams. And we know that our standard deviation is 0.02 grams. Okay, and for A, what we want to do, the first thing we want to do is we want to find the percent of pennies that have a mass between 2.46 grams and 2.54 grams. Okay, so we're given this interval of mass of pennies, and we want to find the percent of pennies that's in that interval. So the first thing we want to do is that we want to take our mean and we want to find out how many standard deviations these two values, 2.46 grams and 2.54 grams, are away from our mean value. Okay, so we're going to first take our mean and we're going to subtract the lower value, which is 2.46, and we get that is 0.04. Okay, and so that's the distance between the mean and the actual value, 2.46. And if we divide that by our standard deviation, we get 2. So we know that's 2 standard deviations below our mean. If we take the top value, which is 2.54, and subtract our mean from it, which is 2.50, we get the same 0.4, and divide that by our standard deviation, we get 2. So these values are within 2 standard deviations of our mean, which means that it falls in this area. Okay, so what we want to do is we want to add up all of the percentages in those areas, which would be 13.5, 34, 34, and 13.5. Okay, and so when we do that, we actually get that the percentage, let's go back to our pen, the percentage 13 and a half and 13 and a half is 27. So 27% plus 68%, that's going to be 95%. So that tells me that 95% of the pennies that that in between these two values of 2.46 grams and 2.54 grams, there are 95% of the pennies. Okay, now what we want to do next is we want to find the probability that a randomly chosen penny has a mass greater than 2.52 grams. Okay, so the first thing we want to do for B is we want to find out how many standard deviations away from the mean is 2.52 grams. So we want to do 2.52 minus 2.5, which gives us 0.02, and divide by our standard deviation. And so that gives us 1. So we know that this value, or this mass of 2.52 grams, is 1 standard deviation above the mean of 2.50. So what we need to do is, if we want to find the probability that a chosen penny has a mass greater than 2.52 grams, then we want all the values that are above. So let's pick a different color. So actually, let me mark where, so if we're 1 standard deviation above the mean, if this is our mean of 2.50 right here, 1 standard deviation above tells me that 2.52 is at this level, because this is 1 standard deviation above. Okay, so this line right here represents 2.52. So if we want the percentage of the probability that a randomly chosen penny has a mass greater than that 2.52, then the percentages that we want to add up are going to be this 13.5, this area right here, all the way to the end. So it's going to be 13.5, the 2.35, and the 0.15. Okay, and so if we add those up, we get 13.5% plus 2.35 plus 0.15. We get a total of, that's 13.5 plus 2.5, that's a total of 16%. So we get a probability that there's a 16% chance that a chosen penny will have a mass greater than 2.5 kilograms. Okay,